Well, so that what we did for the sawtooth wave, we've worked out details of the Fourier expansions for lots of other common waves that you might find in, say, electrical engineering. Typically where you see these waves. So, it's a little hard to read this slide, but there is an equivalent page in the book that's easier to read. And I'm not sure what page it's on. Anyone know?
376.
376? I'm going to write that in right here. This will only work today. This will only work for your class because next class is going to have a slightly altered book probably, and then the pages might be different. So 376. For the triangular wave, this is the wave that goes straight up, then straight down, then straight up, then straight down in straight lines. Again, its complete period is 2 pi. And this notation looks a little bit odd. It's a little different from the previous slides ago. So let me kind of unpack this notation for you. See if you can read that. That's 8 over pi squared. So this is for the triangular. The Fourier expansion is 8 over pi squared. This is the constant term that comes out. The sum from n equals 0 to infinity, right, of 1 over 2n plus 1. I can't read that. I think it's a cube. Can you read that? Squared? Yeah, okay, that's probably right. Cosine of 2n plus 1 times x. Okay. This is, in fact, a Fourier series. But it uses, this n here is being used in a different way. It's not indexing the actual coefficients. All this n is doing is it's indexing the non-zero terms. So if you want to actually find what the coefficients are, the a's and the b's, you should start with this series and just start writing it out longhand. That's what I recommend. So I get 8 over pi squared. And then what's the n equals 0 term? What does it look like? 2 times 0 plus 1 is 1. Squared is 1. So 1 over 1 is just 1. And I get a cosine of just 1x. So here, x is now taking the role of theta. So I'm just changing the name of the variable. So x and theta are really the same. So this is the fundamental term. What's the next term I get in the sum? When n is equal to 1, what do I get?
1 over 3 squared.
Yeah, so this is now 3 squared is 9. So I get a 1/9 cosine of 3x. And then what's the next one I get? N is equal to 2. You got 1 over 25 cosine of 5x. So notice what the 2n plus 1 does. It's taking all the odd numbers. Starting if n is equal to 0 and counting up, you get 1, 3, 5, 7, 9. So here is the expansion, and so on. So all the even harmonics are 0, and I'm left with the odd harmonics. So what does this tell me? First of all, what is A0? It's 0. There is no constant term here. A1 is equal to 8 over pi squared. What's A2? 0. See how they've compactified it? They've only You only have to sum over the non-zero terms, and so they've re-indexed things. They've changed the n to 2n plus 1, so they're only summing over the non-zero terms. So with A3?
8 over 9 pi squared.
Yeah, I'll just say 8 over pi squared times 1/9, and just leave it like that. Okay. And then A4? 0. And so on. And then A5 is going to be 8 over pi squared times 1/25. And so on. So they alternate 0 and then 8 over pi squared times the inverse square. How about the B's? They're all 0. They're all 0. No sign terms here. So that's how you can translate this slide into get the actual coefficients. You just take the sum, start with the sum, and x and beta are the same idea. This is just f of x. They've decided to name the variable x instead of theta. Write it out longhand, and that'll tell you, just by inspecting it, that'll tell you what the coefficients are.
I got a question.
Yes.
I know you kind of hit on it, but I don't quite understand. I understand the odd subs of the A's, but I'm not understanding why we're getting like the evens. Why are they equal to 0?
You get the evens being 0 because those terms just don't show up. If these were not equal to 0, you'd have to have a term there. You'd have something times cosine of 2x. But there is no cosine of 2x in this expansion. So the only way that can cancel is if the coefficient is 0. So it's got to be 0. All right. What else? Well, sawtooth wave. We already saw the rectangular one. So this is the compressed version. You'll get 1 over n, and the minus 1 to the n minus 1. This alternates plus and minus. So what's negative 1 what's negative 1 squared?
1.
Is this 1, and then negative 1 cubed is negative 1, and so on. They alternate plus 1 minus 1. That's what gives you the alternating plus and minus. Square wave, here it is. Great. Absolute sine wave, it's the sine curve, except you take the absolute value of the sine. So this is the function absolute value. This is f of x is equal to the absolute value of sine. So instead of going into negative territory, it bounces back up to positive territory. Here, this is a half sine wave. It looks like the sine wave as long as it's positive, but if it goes negative, instead you just truncate it. You just cut it off and make it 0. This actually shows up. How do you produce this as a signal? Anyone know? How do you produce a signal that looks like this? A diode, yeah, which is kind of like a one-way door, right? So you have an alternating current, which is a sine wave. If you put it through a diode, the diode allows the current to go in one direction, but stops it from going in the other direction. So instead of getting a negative current going in the other direction, it just cuts it off at 0. Anyone know how to get that as a signal?
Which wire? Diode.
This one.
The diode square and the voltage rectifier?
Voltage rectifier, diode,
There was a
square.
diode pattern. I don't remember anything.
Okay, yeah. I don't either. So I trust you.
Yeah, it allows it to go in one way and it allows it to go not back.
It sort of bounces, yeah.
It bounces in.
Yeah, okay. How do you get a square wave? Anyone know?
Type it in a computer.
All right, never mind.
That is one.
It's digital.
All right. So next up is we're going to have to generalize this. So we did the Fourier expansion for a function with period 2 pi. So think of this as a function of an angle. We need to generalize this now to, say, for example, the time domain, where now our signal is a function of time, and we instead of period 2 pi, we're going to have some period t, capital T, which is a time duration here. Now this is in units of time. So this is one of the wave parameters, right? This is one of the time domain parameters. So now we think of the signal as being a function of time. Yes?
Would it still only be a valid t if that's like for one repeat cycle? Does that make sense?
I think so, yeah.
Okay.
Yeah. I think, yeah, if I gather your question right.
Like if you extended the red arrow to cover like half of the third green slash, like that wouldn't be true because you get like a repeat and a half, or I mean a full cycle and a half.
No, maybe I'm not quite. So what you want me to extend the red arrow?
No, I'm saying whenever the bill repeats one time is what you use for t. Like you wouldn't like go a repeat and a half or whatever because it would just skew it.
No, it would have to be the length of an exact repetition.
Okay.
So again, this function, this y of t, has to be periodic. It has to satisfy that it just repeats itself every t seconds. So t here is the period. All right. So how do we get from the angle theta to convert to any period? This is actually pretty easy to do. What you do is you just make the following substitution. Theta is omega times t, where omega is the angular frequency of the wave. So remember, I've got, in the time domain, I have minus sine of omega t. If I leave x equal to 0 off. Well, this is your theta right there. This is for a simple sine wave. But in general, for any complicated waveform, you're still going to have an omega value that determines the number of radians you're going through per second, even though it's a complicated waveform now. But the point is, this is going to repeat, this value will repeat every 2 pi. And so, well, anyway. When we put omega times t in there, now this function is a function of t, and it's going to repeat every capital T seconds, where capital T is 1 over the frequency, which is the angular frequency divided by 2 pi. It's the usual conversion. So let's do this. So I'll write this down. So we have theta is omega times t. So F is omega over 2 pi, right? So plugging that in here, this is going to be 2 pi F times t. So that's another way of writing it. And then t is 1 over F. So we can write this as 2 pi little t over big T. So in each case, t here is the variable. It represents the passage of time. And the other letters are constants. They're constant parameters determined by the actual duration of the wave. Frequency, angular frequency, or period, depending on which one you like. So here we'll just make that substitution here and plug that into the Fourier expansion, and we get this. And when we do that, we have to adjust the integrals a little bit using a linear change of variables, because this is a linear change of variables right here. We're going from theta to t multiplied by omega. Notice that these integrals are dt rather than d theta. Now we're integrating over a chunk of time, and that time will go from, say, negative half the period to plus half the period. So this duration is exactly t, capital T. one period. And again, it doesn't matter where you start and where you end up, as long as the difference in those two limits of integration is exactly t. You get the same value. So here's a naught. What you do is you integrate from minus t over 2 to plus t over 2 of the wave as a function of t, dt, and then you multiply by 2 over the period, 2 over capital T. And you get something similar for a n and b n when you do this. Okay, well, that's fine. What you will get here, actually, is exactly the same values you got with theta. But now, think of this as a function of t. So it doesn't matter what the period is, you'll get the exact same coefficients as you would have if you used theta, and the period was 2 pi. So, just because I have different ways of writing it, we have alternate ways of writing the Fourier series. Here's omega, the angular frequency. You can plug in this next one, which is 2 pi f, instead of omega, and you can get these. Or you can express it with the third thing and get 2 pi over t. There you go. In each case here, t is the time variable. And these are the parameters. So these describe the parameters for the fundamental frequency. So now we have a fundamental frequency, which you can express in any of these ways. So f would be the frequency of the fundamental term. T would be its period, and omega would be its angular frequency. The harmonic terms now will have frequencies that are multiples of this. And so their periods would be divisors of this. We can take one of them for the period. Okay, so we call these are the parameters for the fundamental components of the wave, and we also call these are the parameters for the entire superposition itself. So we take these parameters to mean both. All right. So let's do this with the sawtooth wave. So find the Fourier expansion of the sawtooth wave with amplitude a equals 5 and frequency of 10 hertz. So now we're in the time domain. So this is a frequency of 10 hertz. It's a very low frequency. It has amplitude 5. So 10 hertz, what's the period? If this is 10 hertz, then what's the period?
Seconds per second.
It's 1/10 of a second, because the period is 1 over the frequency. So this is 10 cycles per second, so you get 1/10 of a second per cycle, which is t. So t is 1/10. Let's just fix our units to be seconds. Time units are going to always be seconds at this point. So we have 1/10 of a second. And so half of that period is going to be 1/20th of a second, or 0.05. So from minus a half t to plus a half t, that's the interval minus 0.05 to plus 0.5. It's got to make it up from minus 5 to plus 5, because that's the amplitude. In order for that to happen, you have to take y of t is going to be 100 times t in this interval. Because to get 5 from 0.05, you have to multiply by 100. So the function y of t is actually 100 times t in this particular period, and then that period repeats. All right, so let's find the Fourier expansion. We need to determine the coefficients of the Fourier series. Well, just take the standard Fourier series and make that substitution up here. Theta equals omega t in the Fourier series, and you get the correct Fourier series for the time domain one. So you don't have to do the integrals over again. get the same values. So what you're going to get is, well, the amplitude now is 10 over pi. Let me think. How did we get 10 over pi? I'm a little confused by this. We had 2 over pi before, right?
Yeah.
Okay. So why do we have 10 over pi here? Ah, because 2 over pi. So when we did f of theta, that we assumed there that the amplitude, well, the sawtooth wave that we started with as a function of theta, through 2 pi, that had amplitude 1. This has amplitude 5. So all we do is we have to take the Fourier expansion and multiply it by the amplitude. That's how we get 10 over pi, because we took 2 over pi, multiplied it by 5. Yeah.
Is the amplitude for the Fourier always going to be, I mean, is this always going to be the amplitude times 2 over pi?
Yes.
For that first deal?
For the sawtooth.
Correct.
So this is amplitude 5 times the quantity 2 over pi. And then we write the exact same stuff here, same coefficients, but now we made the substitution, and now we're expressing it in terms of standard frequency, say hertz. So the frequency here is going to be 10 hertz, so the fundamental is now going to be 20 pi t. So 20 pi is the angular frequency in radians per second. And then the next one's going to be 40 pi t, 60 pi t, and 80 pi t. And notice I'm not bothering with the units, because we'll fix our time units to be seconds, and when that's the case, we'll allow ourselves to leave off the units in that case. Okay. Question. Just make sure that you're using the units consistently. Since F is in hertz, which it uses the second as the basic time unit, we have to be measuring t in seconds for this to work correctly. So don't mix, say, microseconds and seconds. Always convert to the same time unit, seconds. All right. Questions on any of that? Okay. So, let's try the square wave, shall we? I'm going to do another example, and I'm going to do this on the board. Well, no, wait. I'll do this first. I'll do this first. Frequency domain. So this is another domain to describe waves called the frequency domain. In the frequency domain, what you're given is a plot of the constituent frequencies that make up the wave. So you're not plotting the wave in space or time anymore. What you're doing is you're plotting it as a function of the frequency. So for every particular frequency, you're going to get you may or may not get a contribution to the waveform. That plot of the frequency contributions as a function of frequency, that's called the frequency domain of the wave. So frequency domain plot, you plot the, so if f is the frequency, so we'll use the standard frequency f, say in hertz. S of f is a function that tells you for any given frequency what contribution that frequency gives to the wave. So we can plot the intensities of SF, of the wave's components, as a function of the frequencies of these components. The frequency spectrum of the wave is the range of frequencies that comprises the wave. The absolute bandwidth of a wave is the width of the spectrum. So let's see an example. So here it is for the sawtooth wave. It's this thing, And now we care about what are the frequency components. Well, we get this contribution from the fundamental term of f. So f here, so y of t, f now is the actual frequency of the wave in question. So at the point f, we're going to get this contribution, which is going to be 10 over pi. So 10 over pi is about like that. Okay, it's a little bit more than 3. The next contribution we are going to get is 5 over pi. So 10 over pi times negative a half. So we'll actually get negative 5 over pi. But we're going to plot just the absolute values. So strictly speaking, this line should be below the axis if we didn't do absolute values. And then the next one is at 3f, we get another contribution, which is 1/3 times 10 over pi, and that's about like that, and that's positive. The function, everywhere else, the function is 0. There's no contribution to the frequency except at the fundamental and its multiples, its harmonics. So everywhere else, between these bars, the function s of f is 0. No contribution at all. Okay, so this is a frequency domain plot of the wave, at least for the first 3 terms. So this goes on forever, and at 4f we're going to get something, and at 5f we're going to get something, and they're going to diminish to 0. All right. So let's find the Fourier expansion of the square wave function without amplitude a and frequency f defined by this. All right, we'll do this after the break. Let's take an early break and come back and do this. How's that? Unless you want to do this. I need to get some coffee.
There's something where,
It is connected in the middle, but not like that.
yeah, that would just be a tree.
No, but there's nothing. It's connected somewhere in. Not like that.
I think it's like, there's so much in sun, I don't know. Because like right
So
here,
so he's not open that next.
like that, they're going to go
You're just
this
going to
one.
resistance.
Yeah.
So the blind leading the blind, and you're just going to end up in a ditch.
I'm gonna start asking questions to try and dumb people down.
Oh, good. That's a busy question.
That's what Jesse Holmes do all the time. But it's just game plan.
That's gangster.
Doing okay. I'm still confused on
That was even terms.
I was trying to
and
figure out.
in B terms
No,
of
it's
this
the
triangle.
second. This is
How
straight from the
why
rail.
the-
Wikipedia has an interesting read about positive terms.
Oh yeah.
One,
What's that? Kind of wrap it up for
and this would be the negative, and then
I was trying to figure out why they can alternate positive things.
here.
I just remember what he said. It just does. It's what it is.
Okay. The cosine and sine function do that
Wow.
periodically. Right? So
My face.
that's like the only thing I understand right now.
That much.
I get it if I did. But we're on that one. I've never really
You don't
done.
want to talk about it right now.
It sucks whenever like 5 minutes into the Monday morning you're completely fucking lost.
Your only hope is that once you start getting homework for a while,
And this has a negative.
that's just not good.
It'll probably click like 3 days after you take the test. Like, oh, I got this. That's what Fourier was all about.
But you're gonna need it for later. Looking at some of those books they gave us. It's good shit.
I'm sure it is good shit whenever you have a clue what's going on.
I don't even read that.
I do too, actually. And I
remember
in my garage.
my wife was asked to throw away from me, and every time I almost do, and I'm like, oh, wait, this costs like $70. And so I did.
I used to have a big one.
Ah, crap.
I had one for like $8.
No, I have a fat
Excuse me.
But I don't know what it is. And that big was like $100-something.
I bet. There's nothing with, that was one of the more fun parts of all. Going to Radio Shack trying to buy something, and then talking to the guy at Radio Shack, and he's like, no clue.
Yeah, I don't know.
I don't know.
I have no idea.
We got these bins in the back.
Yeah. I'm like, thanks, guy.
Thanks, bud.
No, we had that problem, and then we had our own W ladder that would sell it.
Going back to the triangle plate, how do we know if the sorry when he was doing the A's and the B's up there on the bottom half of the there's a triangle or
That's the triangle.
Okay, triangle. So why are the A 0, A 4, and then also all the B's? How do we know that?
From the, I don't know the details of the math because I derived the solution.
So
We know it from the solution because when you write the solution out,
the solution being the second line.
yeah, when you write it out,
the terms.
they're not there. Because if they see the way, well, that's what I think you should know, is that the way the book did it is that the solution notation doesn't include things with coefficients of 0. It just omits them. Like they've massaged their summation so that if it has a coefficient of 0, it doesn't need to come up. It's just not there. As opposed to giving you a solution that says cosine x plus 0 cosine 2x plus 1 9, which would be a viable answer.
Same thing, it's just you have to deal with all these different terms.
So that's how he did it. He basically made there 0.
Actually, that's what
Why they went away in the solution to it.
Okay, so for that, for the A terms, why is it for the B terms as well?
They're cosine.
Oh, because that's the starting point, and all of the, and all cosine. So this has already been boiled down. We can't get cosine and sine.
This is like the final.
But does that make back to here?
My only thing would be that this is an even little part of it because it's symmetrical amount of y. That's negative x.
Okay.
She said it's bad to time.
That's all I
Just that makes it pay, register and everything. Pretty sure before
Negative x equals negative f.
That's good.
Yeah.
So cosine.
So does this even tell us anything?
My wife is really good.
If you're summing all even.
She may not know what this means, but she can infer.
Right.
You know, she knows Spanish. And she knows
Yeah.
What? Fuck you, man. I'm trying to. Not yet. I know it was invented in 1807.
That's cool.
To find out about the heat.
What?
About heat. Heat in a metal plate.
Some people have way too much time on their hands. 24.
He's French, what do you expect? It's not like they were winning wars. Fuck, man, they use pie on here too. Yeah. I flew from Minneapolis to Oklahoma City. Maybe it's Kansas City. I sat next to a French immigrant. And I had some interesting discussions with him. He's like, you Americans, you think that we owe you. And I was like, well, we did kind of save your ass 3 different times. No. I mean, what have you done since then? I'm like, really? You fucking jackass. Yeah. This guy was like,
we used to go all the time on the French town on the border of Germany. Which you gotta go.
yeah. I was telling one. So we were stationed in Fort Riley. There's an Oklahoma City behind Oklahoma. It's going to take less time to drive from Wiesbaden to Paris.
All right. Let's do the square wave and then go on and we'll do the Fourier transform.
About some German.
All right, so square wave looks like this. And here, we're just going to assume that it has some frequency f. We won't even tell you what the frequency is. It's just some f, some positive value in hertz. And it has some amplitude a. So here's what the square wave is going to look like. It's going to go, it's minus a for half the period, and it's plus a for the other half of the period. So remember that 1 over f is equal to t. So this thing here is minus t over 2. And this is plus t over 2. So from minus t over 2, or minus 1 over 2f to 0, it's equal to minus a in this interval. And then in the other interval from 0 to plus t over 2, or 1 over 2f, it's equal to plus a. And then it repeats every period. So there's the period. Let's get a frequency domain plot for this. So to get the frequency domain plot, you need to know the contributions of the various frequencies that you get by the Fourier series. So we have to compute its Fourier series. Well, is this an even function, an odd function, or neither? What do you think? Yeah, it's an odd function. It's actually an odd function. So you tell it's odd if you can take the graph, rotate it around the origin 180 degrees. If it matches up, then it's an odd function. Okay.
I just clicked.
All right. Okay. Well, if it's an odd function, well, I told you that when you integrate an odd function over a period minus pi over t over 2 plus t over 2, you're going to get 0. So in fact, all of the a sub n's are 0. So there are no cosine terms. There's no constant term, and there's no cosine terms anywhere in the Fourier series. But you do get non-zero sine terms. And if you integrate this, you could actually do this integral. You don't need parts to do this. All you have to do is split this integral up into 2 pieces, from minus t over 2 to 0, and from 0 to plus t over 2. Because then all you have is some constant times sine. And you know what the antiderivative of that is. It's minus cosine. And do a linear change of variables, blah, blah, blah. Okay. But to make a long story short, here's what you get. So this is 1 minus cosine of n pi. Well, cosine of pi, cosine of 0 is what, 1? Cosine of pi is negative 1. Cosine of 2 pi is 1 again. Right, so these just alternate between plus and minus 1 as n increases. And so what we get is we have an n in the denominator here. We'll pull out so here in this we're either going to get 2 or we're going to get 0, right? So we're going to pull out 2 from here, 2 over pi from here, and we get plus the a, and we get that 4a over pi. We'll pull that outside. We can factor that all out. And here's what we have left inside. We have sine of the fundamental plus a third of sine of 3 times the fundamental, plus a fifth sine of 5 times the fundamental. So notice here that there's no even b's. The even b's cancel out. I have 1 minus 1. So B2, B4, B6, B8, those are all 0. Okay, and I'm only left with the odd harmonics. The first, the fundamental, the third harmonic, the fifth harmonic, the seventh, and so forth. And they go down as 1 over n. So this is 1, 1 over 1, 1 over 3, 1 over 5, and so on. Okay. That gives you the Fourier expansion for a square wave. And that's already, we've already done that for you, so I wouldn't ask you to do that again. It's already done. Okay, so, but we also want the frequency domain plot. So let's do the frequency domain plot. Do it on the board. So right at F, which is the fundamental frequency, I've got, let's take A just to be 1. I'll just assume A is 1. So I get 1. Let's make that scale a little bigger. So that'll be 4 over pi right there. Okay. So we get this bar going up here. That's for the fundamental. And then that's 2f there. And that's 0. And then 3f. I'm going to get a third of that. I'm going to go out to about there. Or maybe a little bit more. 4f. And then 5f. The fifth. And then over here I get a 7th, and so on. Okay? So that's what the plot looks like for a square wave. That's the frequency domain plot. And here all the terms are positive, so I don't drop below the axis. I just stay above the axis. All right? So let's talk a little bit about bandwidth versus data rate. So if I just take the first 4 terms of the square wave, cut it out like this. What is the spectrum? It's going to be 1f to 7f. I put the 7f term in here. So those are the first 4 non-zero terms. If I just truncate the square wave to those first 4 terms, then the spectrum is the interval where the frequency contributions are non-zero. And that's going to go from 1f to 7f. So what's the absolute bandwidth? It's the length of that interval. So it's 6f. So the word bandwidth actually its meaning has loosened a little bit. So people often say bandwidth when they really mean something else. They really mean data rate. So, things aren't downloading as fast as you'd like them, and you say, well, I just need more bandwidth. That's a very simplified idea. That's kind of a perverted meaning, use of the word bandwidth. So the term bandwidth and data rate are often confused with each other. The absolute bandwidth of a signal is the width of the wave's frequency spectrum. So bandwidth is measured in hertz. This is a value given in hertz, because that's what f is given. Those are the units of f. Now, for the actual complete square wave, the bandwidth is infinite, right? Because I've got infinitely many contributions here. But to a reasonable approximation, if we just take the first 4 terms, then the bandwidth is going to be 6f. Okay. If we take the first 3 terms, the bandwidth is only going to be 4f. If we take these 2 terms, the bandwidth is only 2f. So it depends on how close an approximation we want. The closer the approximation we want, the more bandwidth we need, or the more bandwidth we're going to have for the approximation. Data rate refers to the rate at which bits can be transmitted. So data rate is measured in bits per second, which is not the same as cycles per second. Now that said, there is a connection between data rate and bandwidth. Here's a connection. You can transmit bits of information. You can encode them in an analog signal. This is how data transmission in a wire takes place. This is how wireless data transmission takes place. If you are allowed a certain bandwidth, so if you keep the transmission, you're going to transmit these things using waves. If you keep the waves to a certain bandwidth, everything else being equal, you will be able to transmit some number of bits per second. If you increase the bandwidth, in theory, or at least in principle, you can also increase the data rate proportionally. If you restrict the bandwidth, you have to decrease the data rate. That's everything else being equal. But there's a lot of other factors in here that affect the data rate that independent of the bandwidth. For one thing, you could have a certain amount of bandwidth, and your data rate can vary widely depending on other factors, including how much noise is in the signal. So if noise is injected into the signal, that's going to reduce the data rate, even though the bandwidth stays the same. Okay. The other thing you can do, if you want to reduce the effects of noise, is you can up the power. So you up the power of the signal. So if you're transmitting at a higher power relative to the noise, then the bandwidth can increase again. So the bandwidth, the bits per second depends on the bandwidth, and in addition, it depends on the amount of power and the noise, and it's really the ratio of the power versus the noise, and that's called the signal-to-noise ratio. So S is equal to the signal-to-noise ratio. Or SNR. This is the ratio of the power of your signal divided by the noise. And in principle, the data rate is roughly proportional to the bandwidth times the signal-to-noise ratio. So you can increase the bandwidth by increasing the signal-to-noise ratio. Actually, it's not quite proportional to signal-to-noise ratio. It's like the log of 1 plus the signal-noise ratio. It's not entirely linearly related. But then there are other considerations as well. Once you receive bits on one end, there still might be errors when you go back from analog to digital, so you have to correct those errors. So when the sender sends digital bits through the analog signal, the sender might inject an error-correcting code that the receiver can then use to correct errors. That will also affect the data rate. Error-correcting codes involve redundancy. The actual digital data rate then goes down, sent through the analog signal. So this is what we did in information theory, where we didn't consider that these things were actually transmitted across analog waves. We just looked to see it digital on one end, some noisy stuff, and then digital on the other end. But this is where the noisy stuff comes in. When the digits are translated into analog signals, which are then translated back again into digits on the other side. Okay, so all of these factors affect the data rate, besides the bandwidth. But at least if you hold all of these other factors constant, in principle, the bandwidth and the data rate are proportional to each other. The more bandwidth you have, the more data rate you have. So let's look at some examples. So here is what you get when you truncate the Fourier series for a square wave to the first three terms. It kind of looks somewhat squarish. For example, so in this case, our fundamental frequency is 1 megahertz, which is what? It's mega. That would be a kilohertz. A kilohertz is 1,000 cycles. A megahertz is 1 million cycles per second. So we're into sort of the radio frequency range here. So 1 megahertz. So the period, which is 1 over the frequency, is 1 microsecond, or 1/1,000,000th of a second. So here, the bandwidth, the absolute bandwidth, you're going from 1 megahertz, that's 1 megahertz is the fundamental, that's 3 megahertz, that's 5 megahertz. So the bandwidth is 4 megahertz, 5 minus 1 is 4. And the data rate, in this case, might be 2 million bits per second. Okay. Well, let's say that you double the frequency. So instead of from 1 megahertz, you go to 2 megahertz for the fundamental. Then still the first three terms, then the period goes down to half of a microsecond. The bandwidth is now 8 megahertz. Everything's blown up by a factor of 2. And the bit rate also goes up by a factor of 2. Basically, you're sending everything through twice as fast. You need twice as much bandwidth, but you get twice as many bits per second out on the other end because of that. Okay. So this is identical to the bottom section of the previous slide. Okay. Now suppose we only take 2 terms of the Fourier series. Now your wave looks like this. It's not as good an approximation to the square wave. If you try to transmit bits through here, again, your fundamental frequency is 2 megahertz, but now your bandwidth goes back to 4 because so this is 2 megahertz, 6 megahertz, or 2 megahertz, 6 megahertz. 6 minus 2 is 4. So that's your bandwidth, absolute bandwidth. And so your data rate goes back to 4 megabits per second. Now, a square wave doesn't transmit any information. Okay, because you know exactly what the square wave is completely predictable. That's not what transmits the information. What transmits the information, well, there are different ways of encoding bits as analog signals. One way of doing it is to change the level of the wave for bits. So a 0 bit might be given as a negative level, and a positive bit might be given as a positive level. So it's not a square wave, but it has some irregular shape to it. Well, but the same principle applies there as applies here. If you want to approximate the wave with a closer approximation, you need more bandwidth to do it. You need more terms in the Fourier expansion, and that increases the bandwidth. If you only allow less bandwidth, then you can't approximate the wave as well. And so errors will creep in, and even though you're running this at a high frequency, this will likely cause more errors, which will reduce the data rate because you need better error correcting code and so forth and so forth. Okay. So the FCC allocates by law various chunks, intervals of the radio spectrum to commercial radio. Okay. And so a commercial radio station is only allowed by law a certain chunk of the spectrum, so the width of that chunk is the bandwidth that is allowed. And so radio stations that are that are only given less bandwidth can't broadcast as well unless they up the power significantly, which of course is a cost to them. Or they can transmit at lower power, and but it just won't be that good. So maybe the coverage is not great. So if you're far away, it's going to be staticky. So it's important to know how bandwidth affects things. So we'll talk a little bit more about this later. Now, these are only approximations to the square wave. Like I said, the square wave function itself has infinite bandwidth. To get it exactly, you need infinite bandwidth. But you never have infinite bandwidth in practice. You only have a finite amount of bandwidth. And you have to cut it off. For one reason or another, you cut the bandwidth off at some point, either because your equipment just doesn't, just isn't designed to transmit at certain frequencies because it's beyond the parameters of the equipment, or the FCC won't allow you to do that without, paying a fine or whatever. So you always have limited bandwidth. So you never can get through the signal you want with perfect fidelity. All right. So I'll talk about this more. So you'll never actually get a square wave through. The best you can do is you can cut off the frequency spectrum of the square wave at some finite point, beyond which you either can't do because of your equipment or you're not allowed to do because of the FCC. And what you will get is, instead of a perfect square wave, you'll get some approximation to it. Well, what's true with a square wave is also true with the actual wave you send to transmit bits. You won't get the exact wave perfectly. You'll get some approximation to it, which will be distorted somewhat. And the amount of the distortion goes up as the bandwidth that you're allowed decreases. And as the distortion increases, your error rate goes up. So everything slows down at this point. But we learned in information theory that even if the error rate is quite high, there are error-correcting codes that will allow you to transmit bits essentially error-free at a rate up to the capacity of the channel, but not exceeding it. So the capacity of the channel is proportional to the bandwidth you have. All right. So anyway, enough of that. Any questions on bandwidth, data rate, anything like that? This is kind of qualitative discussion. It's kind of soft. No hard calculations here. All right. So what I'm going to do now is we did the Fourier series, the Fourier theorem, in what's called traditional form, using sines and cosines. We learned on Friday that it's okay to describe a wave, like a simple sine wave, as a sine function. But for mathematical reasons, it's not actually much more convenient to express it as a complex exponential instead. And the modern version of the Fourier theorem does the exact same thing, except it uses complex exponentials rather than trig functions like sines and cosines. So the modern version, which is completely equivalent to the traditional version, looks like this. You have some periodic function f with period 2 pi. And f doesn't even have to be real valued here. So the output of f could be complex as well. It doesn't have to be real. But it is periodic with period 2 pi, and its input is definitely a real number. Well, you can express this as a series of complex exponentials of the following form. And here we have a constant term C naught. So let's start at C naught and go to the right. Constant term C naught plus C1 times e to I theta plus C2 times e to the I times 2 theta, and so forth. So in the exponents, I get multiples of theta times I. Okay. But in addition, I've got negative values of n. So I get a C minus 1 to the e minus I theta plus C minus 2 to the e times e to the minus I2 theta, and so forth in the other direction. So this is actually a doubly infinite sum in both directions. And so we can write that compactly in this form. So n here goes from minus infinity to plus infinity, stays with the integers, of some coefficient c sub n, which is going to, in general, going to be some complex number, some complex constant, times e to the I n theta. So these now take the place of the sines and cosines of n times theta. So again, now I have two fundamentals. I have e to the I theta and e to the minus I theta. Those are the two fundamental terms. And I have a constant term, and then the other terms are the harmonic terms. Okay. But now I've got negative frequencies as well as positive. I have to take them in both directions. Okay. So if you know all the values if you know all these constants, then you get the function out again, because you can just plug them into the sum, and that gives you the function to as close an approximation as you want. So that's in one direction. That's the Fourier synthesis. You know the coefficients, you get back the function. The Fourier analysis tells you how do you get these coefficients in terms of the function. They're uniquely determined by the function. Here's how you get them. You integrate the function from minus pi to pi over one period. F theta times e to the minus I n theta d theta. And then you divide all that by 2 pi. And that gives you each coefficient n. So here, this is the standard where we just take a period. The period is 2 pi, and theta is like an angle in radians. Okay. So notice how much simpler this is. You only have one type of term here. Yeah, it's doubly infinite. But before you had sines and cosines, plus you had this constant term, which was treated separately. Now, everything is on the same footing. All the coefficients are essentially defined the same way, and there's only one formula for the integral. There's only one type of integral. So this is much more unified, much more compact than the traditional version, which makes this, the modern version, preferable for calculations. Okay. So this whole f does not have to be a real value. F of theta could be some arbitrary complex number, as long as this is periodic with period 2 pi, and it's got to satisfy some other things. It has to be at least piecewise continuous, and some other technical things which we don't have to worry about. All right.